Hello everyone, good afternoon. This is Ahmed Shoyeb Raihan. I'm currently doing my PhD in industrial engineering, uh, and I'm also a part of the WVU P2 team. So today I will uh, give my talk on the topic titled Data-Driven Approaches for Understanding and Predicting CO2 Emissions. Here is an overview of what I'm going to talk about today. I will start with the introduction and then I will define our problem. And then I will talk about the existing research gaps and the opportunities we can take advantage of uh, with the help of literature review. And then I will present our research objectives. I'll talk about the data we have used in this work, and I will present the detailed methodology. I will then present our results, and then I will conclude my talk with the contribution we have been able to achieve from this work. So let us start with the context why CO2 matters, who emits the most, and what's the US target. As we can see in figure 1, in 2021, CO2 was about 79% of US GHGs. So cutting CO2 in power, transport, industry, and buildings moves the biggest lever. The middle figure, it shows the top five emitters. We can see China, United States, India, the EU, and Russia, they are among the top emitters. They produce roughly 60% of the global GHGs. And progress in these economies drive actually global outcomes. And in the rightmost figure, we see that the US goal is 50 to 52% below the levels in 20 it had in 2005 by 2030. However, based on the current scenario, unless bold initiatives are taken, getting to this target by 2030 is extremely difficult. Now let us go through a reality check, what's reported, how we are progressing, and what's in the way. Figure on the left shows the current policy for USA. Over 8,000 facilities reported to the GAGRP in 2022. The bar chart on the left shows that power plants as the biggest direct emitters, followed by oil and gas and the refineries, and with other industrial sectors contributing smaller shares. We can also see the current progress. Despite stronger pledges, temperatures keep hitting new highs, and many countries are not on track to meet their NDC targets with current policies. A few are likely to meet them, many are less likely, including USA, and several others they remain uncertain. There are several challenges. Uh, for instance, progress is slowed by energy dependence on fossil fuels, economic trade-offs, technology readiness and scale-ups, financial constraints, policy inconsistencies, and the need for global coordination. We have growing transparency and data, but current policies aren't enough. Hence, our focus on identifying high-impact drivers or indicators and building predictive tools to guide action. So our goal is to build an accurate, explainable CO2 emission prediction model. And we believe that if we can predict well, we can unlock six outcomes. First comes tracking high contributors. We can spot which countries or sectors will drive emissions next and catch the trend changes early. Then for policy and regulation, we can use predicted paths to set realistic targets and stress test proposed rules before they are adopted. We can formulate effective mitigation strategies, prioritizing the biggest indicators and compare scenario impacts. We can allocate our resources in the correct manner by aiming for funding and incentives where the model shows the highest emissions reduction per dollar. Then comes conformance to global agreements. Um, we can check alignment with NDCs and quantify any gap to 2030 or 2050 goals. Finally comes adaptation planning, where residual emissions remain. We can use forecasts to plan resilience and risk management. In short, we believe better prediction model will let us make better decisions. Before moving to the modeling approach, here are some results that we have obtained from a bibliometric study that shows that China and and the USA, they lead in terms of the number of publications related to carbon emission prediction research, as seen from the left figure. And as we can also see from the right figure, that these countries are also leading or taking the lead roles in collaborative research, and they are collaborating with other countries like UK, France, India, and so on. Now, if we dive a bit deeper, the existing research or literature shows us a plethora of works in this area of CO2 emission prediction. We can see that researchers have used different modeling approaches, from statistical models to advanced machine learning models, in predicting CO2 emission. And they have either focused on a single country's emission or conducted multi-country analysis. Besides, we can also see that they have used a number of indicators as predictors in their models. However, we have found some existing gaps which we have aimed to overcome through our study. So uh, Going through the literature review, despite a significant number of studies related to this area, that is CO2 emission prediction, we have identified some gaps, and we are considering them as new opportunities that we can explore in this work. So we have focused on the cluster of 20 countries with the highest human development index to understand region-specific dynamics and influences. We have incorporated a diverse set of features ranging from economic, environmental to energy-related indicators to develop an enriched predictive model. Moreover, unlike existing studies, we have not only focused on one model only, but we employed multiple models in our study to find out the one that is the best fitted one to our existing data. So, summarizing the gaps and opportunities, we have come up with a fourfold research objectives in our work. Our first objective is to incorporate environmental, economic, and energy-related factors for a holistic approach. Next, we aim to pinpoint key development indicators driving carbon emission. The third goal is to build emission prediction model focusing on the data from the top 20 high HDI countries. And finally, our fourth objective is to forecast carbon emission for these 20 countries over the next 3 years once we have developed our model with the most important indicators. So in our work, we have extracted the data from World Bank. We filtered the top 20 countries based on Human Development Index and chose a timeline with all the indicators and ensured that we don't have any missing information or values in the data set. I would like to now clarify one questions that may arise. Why are we focusing on the top 20 high HDI countries? So, firstly, these countries have advanced industries and high energy consumption, and consequently, they have significant levels of emissions. So, first, helping them reduce emissions, we will improve the global scenario. Next comes the quality of the available data. We have seen that these countries didn't have any missing information in the World Bank website, which is crucial for us to build a robust prediction model. Thirdly, as these countries are global leaders, whatever policies or initiatives they take to reduce emissions can be implemented in other nations as well. And finally, we have found out that these 20 countries, they represent a broad spectrum of economies with diverse scenarios, which again is helpful for developing robust prediction models. So when it comes to include indicators that may impact CO2 emissions, as you can see from the table, we have chosen to work with a broad collection of features. Here is what a portion of the dataset looks like. I'm only showing here a part of the dataset. So here we can see only 4 countries, and for each country we have only data for 3 years. But in the original dataset, we have entries of each of all the 20 countries that we chose to work with. And the data for each country in the original dataset, it ranges from the year 1990 to 2014. And for each year, for each of these 20 countries, we have the information regarding all these different indicators or features. Before moving to our detailed framework, let's see a shorter version of our methodology or our framework. So we have followed a two-phased approach in our work. In phase one, we have used multiple statistical models to find out the one that best fits the data and also to find out the most important indicators or drivers relating to CO2 emission. And in phase two, once we have found out what the important drivers are, what we do in phase two is we forecast the CO2 emission over a 3-year horizon um, based on all the important features found in phase one. And here is our entire detailed model framework. It's a bit difficult to visualize this, so let's break it down. Um, let's focus on phase one at first. Here we have five statistical models, and our final goal from this phase is to select the best model and its corresponding best indicators that we will choose to employ in phase two. So we started with simpler models like pooled OLS and then moved to more complex models based on different statistical tests. Here are the five models that we have applied in our to our dataset in phase one. They have different levels of complexity and different types of fits to the dataset. The simplest model is model A, the pooled OLS model, and then we have more complicated models like models D and E that accounts different other traits and information. These are the results from phase one analysis. First, we have the results from the pooled OLS model, that is the simplest model in table 5. And then we have moved to getting results from the two different random effects model with and without the time effects. After that, we found out that we have better models other than the pooled OLS or the random effects models that captures more information about the data. And as a result, we have the results from the first fixed effect model here in table 7. And finally, in table 8, we have the results from the final fixed effect model, which is the generalized linear fixed effect model. We have used these models result in our work. And here we can see there are actually five indicators which are deemed significant by the model. There is a star mark here on those indicators, and we have selected these features or indicators moving on to phase two. Now in phase two, once we have selected the most important indicators, uh, uh, what we do is we apply Sarimax model to forecast the emission patterns for the next 3 years for each country. We have measured the predictive performance of our model using RMSE or root mean square error. So Sarimax is a more advanced version of the model ARIMA. It is the short form of seasonal autoregressive integrated moving average with exogenous variables. Sarimax captures trends, cycles, and also external impacts on time series data. And unlike ARIMA, which only works with past values in time, Sarimax utilizes various economic environmental predictors for an enhanced prediction. So in our work, we have utilized the data from 1990 to 2011 for each country and then made forecasts using Sarimax over a 3-year horizon from 2012 to 2014. Here are the results that we have from phase two. So I'm showing here the results for randomly selected 3 countries. But let's try to see what's happening for one country. So here I'm showing the forecast results for Netherlands. The left figure shows the CO2 emissions from 2012 to 2014 when we have used all the selected features from phase one. So if you remember, we have from phase one, we our main task was to work or to determine the most important drivers, indicators, or features that can best explain the CO2 emission. So once we got those features and feed the Sarimax model, this is how the result looks like. So here As you can see, the actual CO2 emission from 2012 to 2014, it is represented by the orange line here, and our predicted CO2 emission with the selected features or the most important features, it is represented by the red lines. So we can see that the forecast, the actual emission and the predicted emission, they are pretty similar. There is not much difference, but if we did not employ phase one of this study, we can look that the scenario is not, or the forecast performance is not very good. So here again, the orange line, they basically is represent the actual CO2 emission from 2012 to 2014, and with all the features, we see that our predicted CO2 emission, it from 2012 to 2014, this basically is the red lines here, and we can see that there is a significant deviation between this actual CO2 emission and the predicted CO2 emission when we use all the features and not the most important ones. And this figure shows the RMSE scores for all countries using all the features, which is represented by the red bars, versus selected features, which is showed by the blue bars. And we can once again see that we have lower RMSE scores, meaning better predictive performance when we employ phase one feature selection stage. So, to conclude, here is a brief summary of what we have achieved through this study. So, first, we developed a prediction model with a diverse selection of indicators ranging from economic to environmental to energy variables. We worked with an extensive dataset of 25 years for 20 countries, capturing a global temporal and spatial landscape. We have employed multiple statistical models as well as advanced forecasting methods. And our study involved a distinct two-phased approach, unlike other existing studies in the literature. We have validated our results using metrics like RMSE over a 3-year horizon. And finally, we believe that this work will help offer actionable insights for policymakers in their journey towards carbon neutrality. Uh, so here, the first reference is our published paper, and then for your information, I am also showing giving the link of the dataset that we have used. And thank you for your time, and I would be happy if you can share your feedback using this QR code.